All right. So till now we have discussed about the different type of means Bayesian inference. We have discussed in that one we have discussed the experimental distribution and posterior distributions and prior distributions. Right. Till these things we have discussed till now. But as you are saying that you have a issue with the that one distributions, right? Gamma and Weibull and all these things. All right. The message that I received that was that they are not able to understand the Weibull and Gamma and all these distributions, right? So I just want to tell you one thing. When you were a child, so in when you joined the school in your childhood, your teachers taught you about five fruits name, five colors name, five vegetables name, like that they taught you, right? They taught you in that manner, yes or no? When they started to teach you about the fruits and vegetables and all these things, so they ask you that, okay, uh, what are the five vegetables name? What are the five uh, fruits names? What are the five colors name? Like that they started, right? So in that process, if you just realize that there are not only five vegetables and five fruits, right? There are a number of fruits, number of vegetables are there, right? And there may be possible that it may be possible that there are several vegetables or several fruits that you even don't know about them. Yes or no? You don't know about all the vegetables and all the fruits. So, in the same manner, in the college life, in the your master's degree, we just teach you about few distributions. Okay. There are more than 10,000 distribution in the literature. Every day they publish a new distribution. Okay. Every day they're publishing new distributions. So there are number of distributions are there. But thing is that when you use the distribution, why do you use the distribution? What is the meaning of the distribution? Model behavior of a random variables. That is mathematical. Can you explain me in a simple language this one? Okay. Binomial distribution everybody studied. Why did you what is the use of the binomial distribution? Why you are using the binomial distribution? What is the condition for the binomial distribution? If I'm giving you one coin and I'm saying that I'm going to toss that coin, say 100 times, what is the probability of getting 37 heads? Okay, I'm saying that I'm tossing a coin 100 times, and what is the probability of getting 37 heads? How you will find out this probability? Okay, make it simple. I am saying I am tossing a coin one time. What is the probability of getting head? Half 1 by 2. I am tossing a coin two times. What is the probability of getting head? A quarter, right? If I'm similarly, if I'm going to toss a coin 100 times, what is the probability of getting 37 heads? Huh? Half raised to the power 37. Okay, let's discuss about the binomial distribution only first. Then we will go further. Not this one. Okay. Are you able to see it? This is the PMF of binomial distribution. And cx p raised to the power x q raised to the power n minus x. Right. Now comes here when we use the binomial distribution. So the coins we were talking about, right? So we will talk about the coin only. So binomial distribution, I think from the coin tossing experiment, in tossing a coin, let P denotes the probability of occurring a head and Q denotes the probability of occurring a tail, right? Which remains the same in each toss of a coin. Now coin the toss n number of times. If the random variable x denotes the number of time head occurs, then x is said to be follows the binomial distribution, right? So means when you use the binomial distribution, when you have the only two possible outcomes in your random experiment and you are going to repeat the experiment with replacement, not without replacement. All right. In that process, after that, if you are going to do it n number of times, okay, if you are doing out of, sorry, out of n trials, okay, x number of success. Okay, when you have to find out, you have the situation like this. So at that time, you use the binomial distribution. Okay, so binomial distribution was constructed to find out the probability of occurring x number of successes out of total n trials. That was your binomial distribution, the basic one. Okay, similarly, the position for the number of counts. All right, why? Now comes to the basic one, the exponential distribution. Okay, so what x provides you? What is the PDF of exponential distribution is? Lambda into e raised to the power minus lambda x. All right, if x is continuous. So there is a condition that you can fit this distribution when your data is continuous. Here in the binomial, what was the situation? That your outcomes are discrete, right? Your outcomes were discrete 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. These many heads you can get out of 100 tosses. But here it's a continuous data. So after that, you will go to check the shape of the distribution. What is the shape of exponential distribution? This is the shape of exponential distribution, right? So if your data is distributed in such manner, at that time, if they just say, what is the probability if the data is scattered, data is distributed in this manner, okay? So at that time, if they say, what is the probability of x equals to 20? So how you will find out the probability? You will put x equals to 20 here and you should know the value of lambda. So you can get the probability, right? Correct? So that is your exponential distribution. Now comes to the normal. What is your normal distribution? When data is symmetric. So if you just see here, in binomial, in Poisson, in exponential, and in normal, you have the restriction. Correct? Yes or no? Binomial you can use when you have only two possible outcomes. And experiment is under the with replacement. If it is not with replacement, you cannot use the binomial. You have to go for the which distribution? Hypergeometric. Okay. If your experiments are under without replacement condition, so at that time you have the for the same situation you have the hypergeometric distribution. Otherwise, you have to restrict to the binomial. For the position, you have only the condition when you have the number of counts. How many patients are coming to the hospital every day? All right, 10 patients, 20 patients, 100 patients, how many patients are coming? That is your, that will follow the position distribution. Now, third one, exponential. For the exponential, you have the restriction this. If your data is distributed in this manner only, at that time you are going to use this exponential distribution. If your data is normally distributed, that time you will take the bell shape your data is, that time you will use the normal distribution. The shape of the normal distribution will not change. It will remain symmetric. It cannot be skewed. Exponential is a linear failure. All right, it is not going to be negatively skewed or symmetric at all. Right, so you have the restriction here. So in the statistics, we consider a distribution, a good distribution for that particular distribution if it can take the different type of shapes of the PDF, different type of shapes of the survival, different type of shapes of the hazard. I hope you understand what is the survival or what is the hazard. What is survival, what is hazard? What is survival, what is hazard? Hmm? Is risk. Okay. What is hazard rate? Failure rate? Did you heard this name? Failure rate or hazard rate or survival function? Okay. Survival is basically survival or reliability function. Okay. Is that in the reliability function we just defined by RT and survival function we define by the ST. That is very useful in the statistics. Okay. In the daily life. That is basically probability that X is greater than T. Means if any item or any product or any human being is survived up to time t, it is already survived up to time t, what is the probability that it will survive after time t? Okay, probability that X will survive after time t. Okay, so you always interested in the future prediction? Yes or no? If I am I am using this projector, so I am interested in that maybe I will be interested in the study that what is the probability that this projector will be in the working situation after 10 years. What is the probability of that? Right. So that is called as your survival function. Okay. It is nothing but integrating from t to infinity with respect to your density function. Okay. Or if it is discrete, so at the time of discrete, t to t plus 1 because you are saying greater than t. So t plus 1 to x equals to t plus 1 to infinity px. That is your survival function. Okay, for the discrete or for the continuous. Right. So that is very important for us. All right. Second thing is that failure rate. Okay. failure rate or hazard rate. Okay. That is also called as the instantaneous failure rate, not the risk function. It is called as instantaneous failure rate. It is basically, or instantaneous hazard rate. It is basically if any item was working up to time t, okay, any product or any item was working up to time t, or any human being was alive up to time t, what is the probability that it will be fail in the time t plus delta t, where delta t is a very small or negligible time tends to 0. Okay, means right now this tube light is working. Okay, this tube light is working right now in the under the working condition. What is the probability that it will fail in the next microsecond? What is the rate of that one? For means with which rate it will fail? Okay, that is called as the hazard rate or failure rate. So we are interested in that one. So that is basically we defined by the HT, the hazard rate. Okay, it is basically the formula is the simple formula I'm telling. I'm not going to the mathematical one. FT upon ST means PDF divided by the survival. Okay, just see the form of the survival here. Now tell me one thing. What is the relation between the survival and hazard and CDF? Can you find out the relation between the survival and CDF? What is the total probability? Minus infinity to infinity of FT. So dt equals to 1, right? And what is the formula of CDF? If we just talk about the continuous case, that is minus infinity to t of fx dx, right? That is your CDF. FT. What is your survival? T to infinity. If you are going to merge both of them, it will be 1. So means your survival is equals to 1 minus FT, because integral t to infinity fx dx plus integral minus infinity to t fx dx is equals to 1. Yes or no? Then it will be the over the complete range, na? Right? So this is my survival, this is my CDF. I can take this term into the right hand side. It will be 1 minus CDF. Right? So that is the relation between in both of them. So that is my, if I am going to find out, just consider the exponential distribution. What is the PDF of exponential distribution? Is lambda into e raised to the power minus lambda x. What was the survival function, CDF of exponential distribution? We used in the inverse CDF method to generate the random sample. That was 1 minus e raised to the power minus lambda x. That is the CDF of exponential distribution. Yes or no? Right. Now, what will be the survival? Use this formula. 1 minus 1 minus e raised to the power minus lambda x. So it will be e raised to the power minus lambda x. Now comes here to the failure rate. PDF divided by the survival. So it is lambda into e raised to the power minus lambda x divided by e raised to the power minus lambda x. This will be cancelled out. So what you have now? Lambda free from free from x. X is not involved here in the failure rate. Means it will remain constant. Okay. So means it will be constant. All right. So failure rate can be increasing, decreasing, constant, and there is a one more term that is called as the bathtub. Do you understand the meaning of the bathtub? Bathtub, where you just take the bath in the bathtub. So what is the shape of the bathtub? The bathtub will look like this, right? Right. So what is the meaning of this one? Can you interpret this one? This is the failure rate, HT, and this is your X. Can you interpret this one? So here, bathtub means what is the meaning of the bathtub? In the initial period, the chances of the failure is very high, and as the time increase, the failure rate becomes start to decreasing, and then it becomes constant, and it will remain same for a certain period, and then after that it will again start to increase. For example, the newborn baby. Okay, any newborn baby. The chances of the death of the newborn baby is very high. Yes or no? The chances of a death of a newborn baby is high or not? It's high, right? That's why we give so many uh, what we call it. Yeah, uh, we just give so many injections of kind of what we give it. What we call it? Vaccines, right? So we give the so many vaccines to so child should survive from those disease, right? Because the immunity power is not strong. So in the initial stage, when it's a newborn, when it baby is a newborn, what is the time? Time is 0, right? If we just talk about the years, so it is 0 year, newborn baby, failure rate is too high. Okay, as the time started to increase, means 1 year, 2 year, 3 year, up to the 5 year. After 5 years, it is stable because the immunity will increase, right? So means the failure rate is started decreasing with respect to the time. Correct? Are you getting this point? And after 5, up to the age of 45, it is almost constant and it is very low because the chances of the natural death is low. If any accident is not happening or some kind of severe disease is not happening, so the chances of the death is very low and almost stable, right? After 45, what happened? People have the disease, right? And the chances of the death will increase with the time as they will increase to 60 or 70. It will start to increase. Now take the another example from the machinery. When you have the new bike or new car from the showroom, you buy a new car or new bike or car or any item from the showroom, the chances of the failure is very high or not? No, it's very high in the initial stage. That's why they just call it for the service. Yeah, so in first 1 year or 2 year, they ask for the continuous servicing. Yes or no? Right. So that means the chances of the failure is very high in the initial stage when you are going to buy it. After 1 or 2 years, it will be stable for next 10 years. Right. After 10 years, the chances of the failure start to again increase, right? So that is called the bathtub. All right. And when, with respect to the time, the hazard rate is start to decrease, it is a decreasing. When, with respect to the time, hazard rate is going to increase, that is the increasing hazard rate. And for the web exponential distribution, we have seen it is stable. So we need the distribution in the literature where we can see the different type of survival rate. Okay, we can find out the different type of shapes of the survival function, as well as we can find out the different type of shape of the hazard and different type of shape of the PDF. Means if it is exponential, as I showed you here, I can fit this my I can fit the exponential distribution to the data that have only this type of shape. Right. Other than that, if the data is distributed in such manner, if data is distributed in such manner, can I fit the exponential distribution? Not at all. It will not fit. Right. Can I fit the exponential distribution for such type of data? No. I cannot use the normal distribution here also. Right. So I need the distribution that I can put on the different type of data set. If I just see here, I just show you. Okay. This is the code for I made for exponential Rayleigh and Weber. Okay. This is the shape of in the topmost left, sorry. Here, for you it's right. For me it's a left one. The exponential PDF here. This is the PDF of exponential. This is the survival function of exponential. This is the hazard rate of the exponential. Hazard rate is constant, survival only decreasing, and PDF is also positively skewed. Right? Means only one kind of data set I can use here. If I just see the Rayleigh is the generalization of exponential distribution. Okay. In the exponential distribution, what is the PDF you have? This is the PDF of exponential distribution. Lambda into raised to power minus lambda t. So now in the exponential, in the Rayleigh, what you do? You do the square of both of them. Means instead of lambda t, you are going to take the lambda t whole square. Okay. So it will becomes Rayleigh. Okay. If you are going, instead of lambda t, if you are going to take lambda t whole square, it will becomes Rayleigh distribution. All right. So what is the shape of the Rayleigh distribution? Survival is decreasing, but after that it's a constant. Initially it is high, then it starts to decrease, and then it becomes stable, and the hazard rate is linearly increasing. Right. But if you just see in the Weibull, how many types of shapes of the in the this is Weibull and gamma both. How many type of shapes you are seeing here of the hazard? Right, flexibility is there. So that's why we use the Weibull and gamma distribution. Okay. Other distributions also we have that I prepared the PPT here. Okay. So normal, no, log normal, gamma exponential, chi-square, Cauchy, Rayleigh, Burr, Weibull, Pareto, Lindley, Gumbel, okay, Teacher, modified Toplione. All right. So this is the distribution that we developed in last year and power exam. If I just show you this one, what is the benefit of that one? So this is the one distribution that we developed. Okay, new distribution we gave, and we gave it the name of our supervisor here, my supervisor's name, that is Arvind. Okay. So this is my CDF and this is my PDF here. Okay. Why it is so special? Just see how many type of shapes you have. of the PDF. Okay. You will see the kurtosis and skewness. All these things are there. Yes or no? So different type of shape. So it is very flexible. Okay. So that is the use of the distribution here. So you can use the different type of distribution, and if you just see here for the, yeah, hazard rate. What type of hazard rate I was telling you till now? What type of hazard rate we have seen? Decreasing, increasing only. Right? Here, what type of linearly increasing you have? Okay. Then increasing, then dip, then again increasing, then decreasing. All right. Then this is kind of bathtub. Right? For the less time of period, it is kind of bathtub. Right? So that is the use of the distribution. We choose the distribution based on that. Okay. Now comes to the one thing that we were discussing here, the Weibull distribution. So you showed me the one. I think you shown me from the Wikipedia, right? You showed me from the that one. Okay. He showed me this one, this PDF, right? Where they have taken k upon lambda x upon lambda raised to the power k minus 1 e raised to the power minus x upon lambda raised to the power k. Right? This was the PDF. So here you can manipulate your PDF according to your convenience. Here, if you just see one thing, what is your PDF? K upon lambda, right? Into x upon lambda raised to the power k minus 1, right? Into e raised to the power minus x upon lambda raised to the power k. Correct? Here, and what was our prior? Our prior was gamma, right? For theta. Suppose lambda here, lambda is basically your theta, right? Now here, what is the PDF of gamma distribution? A raised to the power b upon gamma b into e raised to the power minus a theta theta raised to the power b minus 1. Right? This will be cancelled out when you will find out the posterior. So it will cancel out because it's a constant. Now comes here. K is a constant parameter. Lambda is the parameter, but you cannot cancel out it because it is in the under the integration. And you cannot merge both of them because here you have 1 upon theta. This term is basically your e raised to the power minus x upon theta raised to the power k. Right? Correct. And this is your e raised to the power a theta. So you cannot merge both of them because base is not same. So base is same, but in the power terms are different. Theta plus 1 upon theta. Right? So here, if you just see one thing, k is constant and theta raised to the power k will be a constant or not? See, theta, you are behaving like a random variable right now. Okay, forget about the prior right now. Forget about this prior. Just consider on this PDF only. Just consider on this PDF. K upon theta into x divided by theta raised to the power k minus 1 into e raised to the power minus x upon theta raised to the power k. Just think about this one only right now. Okay. Here, if you just take this one, theta raised to the power k. So theta is a parameter, so it's a constant value, right? At the initial state, you will give some value of theta, na? Yes or no? And also you will give the value of k also. So constant raised to the power constant, what it will be? It's a constant, right? So can I say it theta 1? Right. So can I write this one as e raised to the power minus theta, and this will be 1 upon theta 1, basically here. 1 upon theta 1 into x raised to the power k, right? So 1 upon some constant value. So it will remain constant or not, right? So can I write it like that e raised to the power minus theta 2, 1 upon theta 1 equals to theta 2 into x raised to the power k, yes or no? So now what will be my PDF form of my PDF? Fx k into x raised to the power k minus 1 into theta 2 into e raised to the power minus theta 2 x raised to the power k. Okay. See, we manipulate these parameters when you have the multiple parameters. So we can get the value of the model, or we can get the value of the log likelihood in a proper way. If you are going to take the log of this one, if you are going to take the log of this term, so here it will be log theta, yes or no? This one, k upon theta, log theta will be there. Why we do such kind of manipulation? Just understand this thing. We have, if you are going to consider this one, what is the log likelihood of this one? You have to take the log likelihood or not? When you have likelihood, you need to find out, na? Or if you are going to find out the MLD, so at that time you need the log likelihood. So in that one, log theta is there. If you are going to fit the data, okay, for the real life data, suppose theta's value is 0.0002. What will be the value of log theta? It will be in the negative, yes or no? The value in that, if the values are in the decimal, log 0.002 minus 8.57. So it can create the problem or not? It might create the problem. But if you just do it 1 upon, if you just do 1 upon theta, so at that time what will be your output? If you are going to replace the theta from 1 upon theta, so it will be 1 upon 0.002, right? So what will be the value? 1000 divided by 2, that is 500, right? So at that time, it will be easy for you for the computation, yes or no? Tell me. I can do this manipulation or not? In the last, it's a constant only or not? In the last, it's a parametric value. When you will change the form of the distribution, okay, you can change it according to you. In the last, what is theta? In the last, what is theta? Theta is a parameter, a constant value. If you change, or you can, if you do the manipulation with the theta, will it make any impact on your final result? Whatever the probability you are trying to find out, or whatever the estimated value you are find out, or whatever the things that you are trying to find out, will it make any change on that one? It will not make the change. It will not make the impact because it's a constant term. Either you just write 1 upon theta or you just write theta. Okay. So here, if just take the example, uh, if you just have the observation, say x equals to 1, 2, 3, 4, 5. Okay, these are the 5 observations. Okay, and after that, I am applying the exponential distribution here. What is the form of exponential distribution? Lambda into e raised to the power minus lambda x, right? What is the mean for that one? For this form, what is the mean? 1 upon lambda. What is the variance? 1 upon lambda square. Did you see this form of the exponential distribution or not? 1 upon theta e raised to the power minus, sorry, uh, e raised to the power minus x upon theta. Have you seen this form of the exponential distribution or not? Right? You have seen this one? What is the mean here? Theta. What is the variance? Theta square. So from here, theta is equals to 1 upon lambda or not? Will it make any change on your study? Only the value of the parameter will change based on the formula of your density. Only the value of the parameter will change. Will it change anything in your future prediction or in your failure rate or anything? Not at all. So this type of manipulation we do according to our study. So here the density function that you took, I cannot merge this one with this term. I cannot merge both of them. So that's why I am just taking the this form of the Weibull distribution. So I can get the posterior gamma again. Okay, again I can get the posterior gamma. So hazard, I want to show you the shape of hazard, right? Uh, yes. See, here we have this is the one kind of shape of the hazard. That is the shape of hazard for generalized Weibull distribution. In the generalized, we have 3 parameters. In the Weibull, we have 2. In the generalized, we have 3 parameters. All right. So with respect to that one, this is the survival function. First one is the survival, second is the hazard, third one is the cumulative hazard here, and this is the form of hazard. So see how many different type of hazard form you are getting, right? And this is your generalized log logistic distribution. Okay, so this is the your shape of your hazard, and here if I just show you one thing, how we describe the distribution, how you describe the different type of distribution. You can make any distribution by your own. So this is the power x gamma distribution that we developed in 2022. Here what happened, they gave one distribution earlier. Okay, its name was the x gamma. So what I did, we were saying that if you remember, I told you that if x follows x follows gamma distribution with a parameter a and b, and I introduce y equals to 1 upon x, so it will be inverse gamma. Okay. If I introduce another variable, that is z equals to x raised to the power alpha. If I do this transformation, so it will becomes the power gamma. Sorry, power gamma distribution. So that kind of transformation people do. Okay, to find out the new distributions. Okay, are you getting this point? What is the use of the Weibull? What is the use of gamma? So gamma and Weibull, log logistic, or your Bohr, or your Lindley, or your teacher, or modified Toplione, all these distribution are basically made for the different type of shapes of your hazard, because we are not only interested in the estimation of the parameter, we are also interested in the many times to find out the probability of your failure or hazard. Why? If we just go there, and this one, what we call it, actuarial science. Okay, actuarial science is related to what? Your insurance, right? In the actuarial science, it is related to the insurance and other things, right or not? Right. So here, what type of data you need to use? In the actuarial, what type of data you mostly have? In the actuarial, you mostly have the heavy tail data. Heavy tail. Okay. Heavy tailed. Do you understand what is the meaning of the heavy tail? Heavy tailed is basically, sorry, if you just see here, when you just draw the PDF, it should have the tail, heavy tail, like this. The figure one, okay, figure one, and in the last three. And here also, if you just see in the last six, in the last two rows, if you just see, you will find the shape like this. You will find the shape like this. That is called the heavy tail. What is the meaning of this one? The physical interpretation. If I just take the example from the medicine, sorry, medical. If I'm going to say that people have the fever, okay, what is the average number of days people should take to cure from the fever? What is the average number of days that people should take to cure from the fever? 2, 3, 5, 7. Right. So if here, if I'm saying that, okay, on the y-axis, this is the number of patients, and on the x-axis, you have the number of days. All right. So this is 5 days, 10 days, 20 days, 40 days, 0. This is 5 patients, 10 patients, 20 patients, 30 patients, and 50 patients. So how this data should be distributed? What should be the shape of this data? It should be look like this. Means most of the patients are getting cure within first 10 days. Only one or two patients are there who are taking 40 or 50 days to be cured. Okay, from the fever, only one or two patients are there who are taking 40 or 30 days to be cured. So means number of observations is very less, but it should go extremely high. That is called the heavy tail. So at that time, what is the shape of the gamma and Weibull, exponential. Rayleigh is a kind of heavy tail, but Weibull is better heavy tail, right? So if the data is a heavy tail, so you can put the heavy Weibull distribution. Okay, so that is the use of these Weibull gamma distributions. Okay, are you getting this point? Why we use these distributions? So that's why we introduce every day we introduce the new distribution so we can fit the different type of data. Data is not only positively skewed and bell shaped. It can be any type of shape we have. Yes or no? We may have the different type of shapes. For that one, we have the different type of distribution where hazard survival is very important. If you just see in this paper you will find here uh, right. So if you just see here in this table, average estimate of the parameters and the survival function and the hazard function using the different method of estimation. So what we were doing after finding the estimates of the parameter, we are also finding the estimates of the survival function and the hazard rate. What is the failure rate here in the second row? Okay, 0.109422, that is the for hazard rate, and that is the value of 0.771759 in the second column. That is the value of your survival rate. Okay, that is your probability 0.771759. That is your survival probability, and 0.1094, that is your hazard rate here. Okay, so that is the use of the variable distribution and gamma distribution and other distribution that we are using. Are you getting these points or not? Do you want a break for 5 minutes? I think it is too much right now for you. Okay, so we just stop the recording for a few seconds. So this is your PDF of your gamma distribution, right? What is the CDF? CDF of gamma distribution is integral 0 to x, okay, x or t, whatever you say, alpha raised to the power beta, gamma beta into e raised to the power minus alpha t into t raised to the power beta minus 1 dt, right? This is your CDF. Can you solve this integral? No. And you need to put it equals to u. Can you solve this equation now? First of all, to solve this equation, you need to solve the integral, but you are not able to solve this integral, so you cannot use inverse CDF method here to generate the random sample. Okay, so that is the restriction of the inverse CDF method. Okay, so now comes to the another one. Here, after the this one inverse CDF method, okay, we have the Markov chain process. So you already studied the stochastic process, right? All of you studied the stochastic process, yes or no? So I am not going to explain all these things to you. Okay, if you want, you can read it in the notes. Basically, here I just give the some introduction of the stochastic process. What is the stochastic process? And after that, uh, what is your arrival time or Markov model? What is Markov process that you already know? All these things, all right. And classification of the stochastic process time or position, discrete time, discrete continuous or discrete continuous. Okay, so in that one, Chapman-Kolmogorov equation, You already know all these things. All right. And step transition probability that you know. You study in the stochastic process or not? Chapman-Kolmogorov equation. That are the initial one. Yeah. Periodicity or irreducibility, ergosity, mixing. That you know or not? Did you read all these things? That is in the stochastic process. You are saying you studied the stochastic process. Huh? You don't remember. Okay. So see, I just give the introduction here of all these things. If you will not understand, I will explain you. Otherwise, you just go through this theory. There are the definitions basically. Okay, of the Markov chain, how we use. Okay, and that is the stationary state. That is the very important thing. Okay, that is very important. That we use in the MCMC methods and all the Bayesian. It is the very important thing. Do you know what is the stationary state basically? So the stationary state is also referred to as the target distribution, limiting distribution, and the various other terms in the Bayesian sense. The stationary state is the posterior distribution. To have a unique stationary state, a chain must be ergodic, that is, possessing the characteristic of the aperiodicity and irreducibility, the convergence of the Markov chain to a stationary distribution. One can use the package coda of our software to check the stationary state. It means basically like that. Right now, whatever the method we are going to study, all these methods are basically approximation method. Okay, when you are not able to find out your posterior distribution in the closed form, so at that time to find out the estimates of the parameter or to generate the random sample, you need to use some approximation method. Okay, so that in that approximation method, they should reach to some limiting distribution or some targeted distribution that we are supposing to achieve. So how to check that it is going to achieve that one or not? So for that is called as the stationary state. Okay, means kind of stability is there. All right. So in that one, we are going to use the Markov chain Monte Carlo technique. All right. So Markov chain have the many application in the areas of bioinformatics and other areas. Major limitation of towards in the Bayesian approach, obtaining the posterior distribution is often required. Okay, when you, so if you just seen that you are saying that when you were using the different form of the variable distribution, you were not getting the posterior in the closed form. So how you will estimate the parameters at that time, and how you will generate the random sample from the posterior distribution if you want to generate the random sample. All right. So integration of high dimension function, this can be computational very difficult, but several approach for the direct integration can be available. All right. So here we have the Smith 1991, Turner 1996, and MCMC method can be used to simulate the direct growth from the some complex distribution of interest. All right, so in that one, MCMC approach are some name because of the uses of the previous sample to randomly generating the next sample values. That's why we are giving the name MCMC here. All right. In generating a Markov chain, there are several MCMC techniques in the literature. Some of them are gift samplers that we discussed earlier. All right. If you just remember in the gift sampler, what we were doing, we were generating the random sample from the initial guess. Then we were using that initial guess as the known value, and we were generating the another one. And then we were using that another one as the again the initial one, and we were generating the another value. That's how we were using the GIF sampler, right or not? Right. So the GIF sampler Metropolis algorithm, Metropolis hasting algorithm. Metropolis hasting algorithm is the generalization of the Metropolis algorithm and importance sampling and others. So in that one, what is first one is the Monte Carlo integration. What is Monte Carlo integration is basically the original Monte Carlo approach was a method developed by the physicists to use the generate random number to compute the integrals. Suppose we wish to compute the a complex integral I equals to integral over the range of a to b hx dx. Okay, here hx is a function of x. Okay, hx is our function that we want to solve. Okay, hx is our function that we want to integrate. In the posterior, what we want to integrate in posterior density. In the denominator, we always have the integral, likelihood, and prior, and then we do the integration over the range of theta, right? So here we, instead of Lx into g theta, we have hx. Okay, if we can decompose hx into the production of a function of fx and the PDF px defined over the integral ab, then we have integral a to b hx dx equals to integral a to b fx into px dx. All right, means if you have the hx is your function, okay, hx is your function that you want to integrate, that is your overall function. If you can write it in the form of fx, fx is the function of x, any function of x, and corresponding to that, x has the PDF, that is your px. X has the PDF, px. Fx is not a PDF. Fx is not a PDF. Fx is any function. Okay, fx is any function of x, but px is the density function. So if you can write it in this form, so what it will be? The expected value of px of fx, yes or no? How do you define the expectation? Expected value of x. What is the expected value of x? Integral over the range of x into fx pdf dx. And how you find out the moments? X raised to the power r, integral x raised to the power r fx dx, right? And if I want to find out the expected value, and if similarly if I want to find out the expected value of gx, any function, how I will find out the expectation? Integral gx into fx dx, right? So in the similar manner, we have this expectation. Okay, expected value of px fx, expected value of fx with respect to the density function px. So that is our approximation method. Okay, so that should not be the accurate one, but the approximated one. Okay, so the integral can be expressed as and the expectation of fx over the density px. So thus, if we draw the large samples x1, x2, xn of the random variables from the density px, how you will solve this one? Okay, how you will solve this one? Expectation is basically the mean, correct? Expectation is the mean, right? So you can generate the random numbers from the px, density px, right? You can generate the random numbers from the px, yes or no? So if they are the large enough numbers x1, x2, xn, and you are going to take the mean of them, okay, if you are going to take the mean of them, means you just put all these values here in the function, if we will put these values in the function and you take the mean, that will be approximate to the your integral. Basically, what we are doing here, we have the integral a to b hx dx, right? Then we are finding one function that should be equivalent to the, oh sorry, px into fx. That can be approximate by this form. Then we need to find out, now we need to find out this integral a to b px into fx dx. So here that is the expectation basically, sorry, of fx, right? So now what we will do, how this approximation method works, now we use this px, this density function, and we will generate some random numbers, say x1 x2 up to xn. Okay, n should be large, n should be very large. Okay, as we did in the gift sampler, if you remember, we run for the 2 million times, right? So like that, you need to run that one. And then what you need to do, whatever the values you have generated from here, you just put it in this function. You just put inside this function. Whatever the function is there, put it there, and that will be equivalent to the your integral a to b hx dx. Okay, when you are going to find out the mean, it will be the mean of, it will be the value of the integral a to b hx dx. Okay, that is called as the Monte Carlo integration technique. Okay, but for that one you need to find out one distribution px here. Okay, so that is your integration part. Then after that, what you need to do, this referred as Monte Carlo integration. Monte Carlo integration can be used to compute the posterior distribution required for a Bayesian analysis. Consider the integral here, Iy. Here we have the integral Iy, integral over the range of y, fy given x. This is your likelihood, right? This is your prior px dx. That you need to integrate in the denominator. Yes or no? Right? Which is approximate by 1 upon n summation I goes to 1 to n fy given xi. That is the your function that we are writing right now. Okay. So if you have the posterior distribution, that is likelihood Lx plus theta into g theta divided by integral over the range of theta Lx plus theta into g theta, right? So here Lx plus theta into g theta will divided by, here consider this as your distribution, right? Your function fx. So 1 upon n, I goes to 1 to n Lx plus theta. Theta I follows the g theta. All right. So what you are going to do, you will generate the random numbers from your prior distribution. You will generate the different theta. Okay. So what you are going to do here, you are going to integrate Lx curve, theta is there, and g theta. Okay. So g theta is the prior distribution of theta, right? So you will generate the different theta from here, theta 1, theta 2, up to theta n. A large theta you will generate from your prior distribution. Okay. Are you getting this point? Are you getting this one? So you use the prior distribution because you have the prior distribution are given. So you will generate the theta from the prior distribution theta 1, theta 2, theta n, and then you will take the mean of the your likelihood. In the likelihood, you will have the, so for example, if I just take the example, we took the example of position and gamma, right? And the posture was gamma only, right? So if I just take the that example, so if I just use, suppose I'm not able to solve this one, okay? So how I will do it? So what is my likelihood? What will be my likelihood? E raised to the power minus lambda, lambda raised to the power x upon x factorial or theta, you can say, right? So I goes to 1 to n. That is my likelihood. So it will be e raised to the power minus n lambda into lambda raised to the power summation xi divided by product of I goes to 1 to n xi factorial. That is my likelihood, right? Now I am saying that lambda is following gamma distribution with parameter alpha beta. So I will give the value of alpha beta here as we did earlier, right? So we can get the value of different lambda. We can generate the random sample from gamma, R gamma or not. What is the code to generate the random numbers? R gamma and alpha beta, right? Correct. So you can generate the different lambda here from here, lambda I. So n lambda you can generate. So here they already provided you the value of xi. X is given, the real data set. Yes or no? Right. So you will put each value of lambda here. So you will get the value of likelihood or not. If I just do it like this, suppose x is 1 to 10. 10 observations I am taking of x. What will be the likelihood of exponential Gaussian distribution? Lambda raised to the power n lambda raised to the power summation xi, right? Sum of x, right, into e raised to the power minus lambda x. So it will be e raised to the power minus n into lambda. What is n? N is your length of x. Okay. The entire term in the bracket, what is your in the division? Product of your, sorry, factorial x, right? That is your likelihood. Correct. Now I'm going to find out the lambda from the R gamma distribution. How many I'm going to find out? say I am saying m is equals to 10,000 comma 4, right? So now this should be, this likelihood should come after this. Okay. So what I need to find out now? The mean. So that is basically 1 upon m into sum of likelihood. Yes or no? That is the value of theta. In the last, whatever I am getting, this is the value of theta. Integral, when you are going to do the integral over the, so not the theta, when you are going to do the integral over the range of theta in the uh, your problem where experimental distribution is uh, Poisson and prior is gamma. So at that time, when you are going to do the integral in the denominator to find out the posterior distribution, so that is the value of this, that integral. Okay. Are you getting that point? What I'm saying? In your Poisson problem, we solved the Poisson problem, na? Experimental distribution by the Poisson distribution and prior was gamma. Do you remember that? In that one, when you were solving, sorry, uh, hierarchical Bayes. So before the hierarchical Bayes, this question was there. Yes, in this question, xi was the position and theta was following the gamma distribution, right? So when you were finding the integral under the denominator, this one, this integral, what is the value of this integral? Okay, because we are able to solve this integral in the closed form, so we solved it. But if we are not able, if we were not able to solve, how you will find out the value of the this integral here? Okay, this integral. How you will find out the value of this integral here? So that is the value of, so this is the value of that integral by the Monte Carlo integration method. Okay, by the integration method, if you just do it, that's one. Okay, now it is more approximate, more closer. Okay, that should be very large. Now it will not change much more, even though if you are going to increase the zero here. Approximately same. Okay, because it is enough large, right? Because it is enough large, so it is not going to change much more. All right, so that is your Monte Carlo integration method. Hmm? 2 and 4 is the hyperparameters of your prior distribution. Yeah? No, that is not given. That we are taking from our side, means it can change according to your study. That is the hyperparameters. Basically, hyperparameters, you are not sure about the prior. So how can you sure about the hyperparameters? Hyperparameters depends on your study. Okay, I told you how to take the hyperparameters for the non-informative and informative, if you remember. 0.001 for the non-informative, and it should change according to the mean for the informative, right? I told you earlier in the detail. So, so what we are doing here in this integration method, so Lx curl theta divided into g theta. So instead of this integral, we are writing 1 upon n. summation I goes to 1 to n Lx theta that we found here, that we find here, this one. Okay, 1 upon m sum of likelihood. Okay, this one, and where theta I follows the g theta, that was our prior, that was gamma. So what will be your estimate of your theta? What will be your estimate of theta under the self? That is the mean of posterior distribution. So what it will be? Integral. Again, you need to do the integral in the numerator, multiply by theta into Lx squared theta into theta divided by, oh sorry, into g theta divided by the integral Lx squared theta into g theta with respect to theta. So what it will be? Expected value of Lx squared theta into expected value of theta I. Okay, expected value of theta I into Lx squared theta, if you are not able to solve. So that will be your mean under the self. Okay, if you know that one. Here, what we are doing, if you don't know how to solve it, so just take the integral a to b gx, so divide by and multiply by b minus a. So b minus a will come out as the constant. B minus a will come out from the as a constant. So what it will be? B minus a. That is your uniform distribution over the range of a to b, right? A to b is the range. Gx is now the function, right? If you just take it here, the hx that you are taking, if you just replace hx with the gx, so what is the simple way? Just take 1 upon b minus a. So 1 upon b minus a is your uniform distribution. Find out the estimate expected value of gx under the uniform distribution over the range of b minus a. So here we just took the example. Sorry, example is not here, but it should be, yes. So this one, integral 2 to 5 x raised to the power 3. How you will solve this one? N equals to 100. Just take a equals to 2, b equals to 5. So generate the random numbers, 100 random numbers over the range of, from the uniform distribution over the range of a to b, that is 2 and 5, and then find out the mean of this one. Whatever the x you have generated from the uniform distribution, put here and find out the mean, and then put it into the I equals to b minus a into y. That was here. B minus a into mean, right? So put it here, you will get the value of integral. Okay, you will get the value of integral. So that is your Monte Carlo integration method. So that is the estimated Monte Carlo integrated error, standard error under the Monte Carlo integration. That is your 1 upon n into 1 upon n minus 1 summation I goes to 1 to n fy given xi minus estimated value of yi and the whole square of that one. That is your standard error, right? Time's up, or we have a time now? Okay, time's up. So in the next class, we will discuss the importance sampling and other things. Okay. Thank you for this. If you have any question, you can ask right now.